Okay. So what I'm planning to do today is talk a little bit about material behavior. So just to put it back into context, we were trying to solve this problem. Um, so we started to by saying that we want to find the displacement field at each and every point in our structure given all this loading and geometry and all that. And then the first the first step that we took was to try to find out what is the governing differential equation. And if you remember, I said that you have to enforce the equilibrium in the deformed configuration. So if you go to the deformed configuration and pick out a cube, which hopefully you guys did also for your second homework problem, that would be similar to this. The equation that you get after summing the forces uh, is this divergence of the Cauchy stress plus body force. Now body force, some of you were asking me, it's something like self-weight. So this equation must hold at all times everywhere. Okay. So in this derivation, I just talked about sum of forces. Do I need another equation? Sum of moments, right? So this is a finite sized uh, piece of a body, and when I take the limit, it will go to 0. But since it is finite sized, I also need to sum the moments, right? So you can probably add this to your handouts as well. What do I get if I say that the sum of the moments has to be equal to 0? What equation do I get when I say that sum of the moments about all the three directions, that x, y, and z, if sum of the moments has to be 0, does anybody remember what equation you would get? Right, so that just says that the Cauchy stress is symmetric. And your number of unknowns gets reduced from 9 to 6. So yeah, these are the equations that we are going to be solving. And in this part, I hope that most of you have seen it in some form of other, some form or other. So hopefully this is not new to anybody. Then we started to talk about vectors and tensors, and this might be new to some people. But I think the main part that's new to uh, to a few of you who have not taken mechanics before um, is this. This is the description of the kinematics. So the previous section was all about kinetics. This is all about kinematics. How do we describe the deformation of the system? This might be new to those of you who have not taken 570, but again, the only thing that you need to sort of remember here is that this is all just vector calculus, and all we are trying to do here is to express or distinguish between the deformed and the undeformed configuration. If you don't distinguish between them, then you just boil down back to hopefully what you've learned, all the linear theories. So this kinematics, and we talked about strain measures, and the strain measures that we are going to be using frequently. One is this green Lagrangian strain, and the other strain that you are hopefully used to is this uh, linearized strain. So, and then we talked a little bit about the compatibility equations, and we said that if you start out from the map, then compatibility is automatically satisfied. You don't have to worry about these conditions. On the other hand, if strain is a part of your solution, then you have to make sure that it satisfies some conditions of compatibility so that it corresponds to a real displacement. Okay, so what I'm going to talk about today is material models. Why do we need material models? Because again, if you remember, we had this equation to solve, and we decided that we know that stress is some function of strain, and strain is some function of displacement. So we are going to talk about this material model. Now, at the same time, you also need to realize that this material model can be different at different points of the beam. So for example, this is my bridge beam, and it has some reinforcement down in the towards the bottom fibers. So the reinforcement has a material steel, and the rest of that is concrete, and you need to distinguish between those two types of materials also within your body. So the point here I'm trying to make is that at each and every point you have to satisfy this equation, and you have to satisfy the strain displacement relationships. So the number of equations that you have in this case is 3 for the equilibrium. And remember, this is 3 equations because divergence of this tensor will be a vector. Okay, this is internal force plus external force is equal to 0. Similarly, you have this strain displacement, total of 9 equations we have. But the number of unknowns is 3 for the map or the displacement. If you know the map, then you can find the displacement. If you know the displacement, then you can find the map. So 3 unknowns right here. You have 6 unknowns for the strain, and you have 6 unknowns for the stresses. So you have 15 unknowns and 9 equations, which means that you have to find 6 more equations. And those 6 equations are nothing but the relationship of stress to strain. And the reason that another reason that we need to find these material models is because all these problems are highly indeterminate. So if you remember from maybe structural analysis, whenever you had an indeterminate structure, you had to assume some sort of material properties before you could actually find any displacements or those kinds of things. So actually, if you consider a rigid body, a finite size rigid body, and if you apply some forces, this is a highly indeterminate problem. You cannot determine the state of stresses for a rigid body. You need some material constitutive laws. So what we need here is this stress as a function of strain. So how about this? How about if I say stress is some scalar times the strain? Can I do that? Is that what kind of a model would this be? I can surely do that. I needed 6 equations. I've just created 6 equations, right? But this has to represent some real material. So when you go to the lab and you say that, okay, I'm going to apply this type of a strain and measure what stress I'm getting, then this simple relationship will probably not capture anything, right? So there are different ways of coming up with these material models. So this relationship is not as simple as I just stated it, but we'll take a look at how this gets modified under different types of theories. So when we are developing these material models or constitutive theories, we have to keep in mind certain principles. One is this principle of determinism. Does anybody know what, or has anybody heard of that? So what this is saying is that if you go to any point in your body, so you go to some point, the material behavior of that point depends only on its own history. So whatever has occurred in the past, at that point, the current material behavior will depend only on that and its own location. That's all that this principle of determinism says. I mean, it seems fairly obvious that how can something depend upon something in the future? So, but mathematicians make a big deal out of this. Another important principle is local action. So what does that mean? It means that if you go to any point in this body, the behavior of that point is going to be governed only by that point and perhaps a small radius around it. So the material action, the stress, is a function of local strain. The stress at this point does not depend upon the stress at some other point. They are connected only through equilibrium equation. The stress, the material property is not dependent on long range things. And third very important point is observer objectivity. What that means is that if I'm looking at a point in this body, somebody else comes around and takes a different look at that body, then the prediction that I make using a material model, so let's say I choose my material model, I'm looking at this point, I find some stresses, find the strains, and using my material model, whatever material model I developed, I find the stresses. Some other person comes, takes a different look at the point, they find their own strains, and using the same material law, they find their own sets of stresses. But now if I transform those stresses into my coordinate system, they should be equal. So that's observer objectivity. Sometimes it is also called material frame indifference. What that means is if I look at the material from this angle versus if I look at it from another angle, it should behave the same way. This function should behave the same way. The exact functional form may not be the same, but in the end, you should get the same result. And finally, it must follow some laws of thermodynamics. What does that mean? So does anybody remember what is the first law of thermodynamics? Conservation of energy, right? Um, if if you apply some stresses to your body, it should not be creating energy, right? We cannot solve the energy problem of the world just by making a material model. So first law of thermodynamics says that when you do work on the material, loading and unloading, it should not be creating energy. Second law of thermodynamics, it says entropy. Entropy has to always increase in a closed system. So these are not that simple things to come up with, but we'll stay with one of the models that automatically satisfies these two laws. And I'll talk about that in a little bit. So what are some of the classes of these material models? And if you talk to 10 different people, they will give you 10 different answers for different classes of materials. So the way I like to think about it is that one huge class is elasticity, and whatever is not elastic, just lump it into inelastic. Okay, and some of the examples of elasticity are here, but let me actually show you. So this is the Abacus theory manual. How many of you have already downloaded the student version of Abacus? Okay, not many of you. Yeah, it's coming up in a couple of weeks. I'll give you a small problem or introduce Abacus to you. So you better, I think on the syllabus there is a link. Just download Abacus student version and install it on your computers. So this is the theory manual for Abacus, and if you look at how it is arranged, there is this fourth chapter which is all about material constitutive theories. The first couple of things are mainly about how to solve different equations. We've talked about that a little bit, but procedures and elements is all this course is about. So if you go to this and take a look at this overview, then right here it says this one of the simplest models is linear elasticity, and this is the same relationship that says stress is some function of strain. But if you look at the overall things here, you can see some elastic models, large strain elasticity, and versus some plasticity models. So this is just trying to give you some overall picture of what these models are. And if you go to any of these models, they all follow these kinds of notation. So when you're using Abacus, that's why I'm emphasizing that when you're using Abacus, when you go out in the field, you're running some analysis problems, and you want to model a certain material, you have to be able to look at these theory manuals and try to understand where or what parameters to enter, what things you need. So, all right. So the classes of materials that I'm talking about here is one is a hyper elasticity. So this is a rate independent material. What that means is if you load the material slowly versus if you load it very quickly, the stress after equilibrium will be the same. Okay. There is another form of elasticity called hypo elasticity, which is the rate form of the same thing. So, for example, here you can express this as in this fashion, where this C with a double tilde is actually a fourth order tensor. So has anybody seen this notation before? No? Okay. So now actually this is a little bit interesting, because if this is a fourth order tensor, it is acting on a second order tensor and it produces another second order tensor. So that sort of even more generalized definition of the tensor is that it acts on a tensor and produces another tensor. So this might be a little weird to hear, but essentially this is how we can denote the relationship between stress and strain. And the hypoelasticity model, you express it in the rate form, meaning if you take the time derivative of this equation, then you come up with this. So and then there is another form of elasticity called viscoelasticity. This is a rate dependent. This is a rate dependent model where it actually makes a difference with what speed you are loading your material. So in the inelasticity regime, there is rate independent plasticity, which if we do get time towards the end, I'll show you a simple small strain model for that. Plasticity, what hopefully you have some intuitive notion of plasticity, that if you keep on loading it a material, it goes up to a certain elastic point, and after that it yields. So when it yields, it cannot carry any more, depending upon the type of plasticity, it cannot carry any more load, and the material starts to flow at that point. People have also come up with damaged plasticity models. What that does is, for things like concrete, highly heterogeneous, there are cracks, crushing, all kinds of phenomena are going on. So for those types of materials, people try to have some sort of a damage parameter that can capture the cracking behavior or those kinds of things. And then similarly, similar to viscoelastic, whenever you have this word visco, it means there is some sort of a rate dependence. Okay, so rate dependent plasticity. So what we'll stick to is hyperelasticity, and what hyperelasticity is all about is this right here, the definition of hyperelasticity. If you go to a material point, and if you can find a scalar function to that that defines the potential energy stored at that point, then you can call this material a hyperelastic material. Obviously, again, this is a model. No material in the real world is hyperelastic to in every regime, but this this material model says that if you can find a scalar function at every point, then you can call this material a hyperelastic material. And this scalar function, it's a scalar function of a vector and a tensor. So this first vector is a position. So obviously, as you can now go back and imagine here, we can have different strain density at different points in our structure. In the concrete, it will store less strain energy. The steel will store more strain energy per unit volume. So this is a strain energy density function. And if you remember from perhaps undergraduate or even high school, when you might have taken a spring, and if you extend it by delta by applying some force F, the strain energy or the potential energy stored in the spring is given by the area under the load deflection curve, and that was expressed simply as half k times delta squared. So a very analogous thing happens here. If you go to a point in your body, you can try to imagine that at each point in your body you have these small three-dimensional springs, which, if you go to a point in your body, find the strain, it can be related, you can find the scalar energy density function using this expression. And once you have this energy density function, then there are a couple of consequences of this. First, that if you load your material in one way and reach some point, some state of stress, versus if you load your material in another different way and reach the same state of stress, then the energy stored in your system is still going to be the same. So what that means is it is path independent. Okay, and whenever you have this kind of a strain energy function, you can calculate the stress by taking the gradient of this function. This is a scalar function. I can take its gradient with respect to a tensor, and in components, what this means is this. So for example, if I wanted to find the ij component of stress, I would take that strain density function and take its derivative with respect to the ij component of the strain. So we'll take a look at a couple of examples on this, but okay, so this was the strain energy density function that defines whether your material is hyperelastic or not. So for finite deformations, this hyperelasticity holds for finite deformations also. But in finite deformations, the function, the strain energy density function is a function of either your F, which we talked about last time. F is the deformation gradient, or it is a function of C. Now C was F transpose F, which was a deformation tensor. So now if you take a look back on the first page also, what I said here, on this page I said that sigma, the Cauchy stress, is the derivative of this function with respect to linearized strain. Okay, so what that means is that Cauchy stress is work conjugate. Have you heard that term before, work conjugate? That if you take half times small strain, linearized strain, times the Cauchy stress, then you get a measure of the strain energy. In the same way, for finite deformations, the work conjugate of F, the deformation gradient, is called P. P is the first Piola-Kirchhoff stress tensor. We'll not worry about that just yet, but just to complete the notes here, I can also mention that the work conjugate of C, or equivalently of E, is S, Now S, you might have been using S as the Cauchy stress in 570, but here S is called the second Piola-Kirchhoff stress tensor. And these are nothing but actually transformations from the final deformed configuration back to the original undeformed configuration of your Cauchy stress. So, but anyway, so this is, you can come up with these kinds of scalar functions, and you can create a hyperelastic material. But you would have to calibrate your material model by doing experiments in the lab. Okay. Now, so some of the functions that people use, what they try to do is try to express this function in terms of the invariants. Do you think, why should we express these functions in terms of invariants? Right, so they're not dependent upon the coordinate system. If I look at it, I have some measure of strain. If I calculate the invariants and somebody else looks at the same point, they calculate their invariants, then coordinate independence says that my invariants should be equal to their invariants. And then if I define a function based only on the invariants, then that would be a coordinate independent function. Some examples of these materials. So you remember what is the first invariant of C? That is something we talked about last time. So first invariant of C was, yeah, the trace of C, which was, if you remember, taking a small unit cube, deforming it to lambda 1, lambda 2, lambda 3. If there is no strain, then lambda 1 is equal to lambda 2 is equal to lambda 3. So if there is no strain, what is the value of IC? It's 3, right? If lambda 1 is equal to lambda 2 is equal to lambda 3 is equal, they're all 1, then this becomes 3. So when I say IC minus 3 here, when I say IC minus 3, then if there is no strain, this term will go to 0, which seems reasonable, because if there is no strain, then there should be no strain energy. Similarly, if you take a look at the second invariant, so the second invariant is lambda 1, lambda 2 square, and so on. But if all of them are 1, then this is 1 square plus 1 square plus 1 square, this is also 3. So again, under no strain conditions, again under no strain conditions, the second invariant would also be 3. So this term would also go to 0 under no strain conditions, and you would have the strain energy density to be equal to 0. So what is the default value of the third? You don't have to actually stop here. This is a class of materials, so you can also include the third invariant, and the third invariant is determinant of F. So that is lambda 1 times lambda 2 times lambda 3. So you can also write another term in terms of I third invariant minus 1. The default value of that is 1, right? All right, so most of the times we deal with materials that are isotropic. Now, isotropy is a material property. Okay, it's not a physical principle. So you might consider a material like wood, which is anisotropic. It has fibers running along one direction, and it is very strong in that direction. If you bend it in any other direction, it doesn't. It bends more easily. So those kinds of materials are anisotropic. But on the other hand, if you have a material that is behaving exactly in the same way in any three directions, then that material is called isotropic material. And one way to express the energy function for an isotropic material is by actually not expressing it as in terms of the invariants, but actually expressing it as a different function of uh, of of the eigenvalues of your stretch tensor. So you calculate your eigenvalues of the stretch tensor, and if this condition holds, what does this condition say? That I have some function of lambda 1, lambda 2, lambda 3. If I switch the order of lambda 1, lambda 2, meaning uh, if I if I take my material and flip it around in a different orientation, then does it behave the same way? Flip it around in another orientation, does it still behave the same way? So if this condition is satisfied, then the material, we can call it to be isotropic. Okay. And one example of a small strain, now example of a small strain material is the Hooke's, what you might be used to calling the Hooke's law. I don't want to call it a law because I like to call it a Hooke's model. It's not a law, it's a material model. Okay. So the way that we express this Hooke's model is that the Cauchy stress can be found from the strain using this expression. Um, Here, this actually should be small strain. So this is linearized strain, and note that this includes two constants. Okay, so for any small strain, isotropic, linear elastic material, you can always express that relationship with only two constants. And the good thing about having the least number of constants is that you have to conduct least number of experiments to find out those two constants. Okay. Otherwise, every material constant that you introduce into your model, you have to conduct some sort of an experiment to calibrate it with whatever you're seeing in your experiments. So here I'm just listing out some of the common relationships. This might also be, this is from the Gunstad's book, one of the homework problems on chapter 4. So this lambda and mu, they are called Lamé parameters, but there is no direct way to, there's no good experiment to measure these properties. So what people normally do is use either a set of C and nu. C is the Young's modulus, nu is the Poisson's ratio. So you can conduct experiments to measure these, and using the values of C and nu, you can actually go back and calculate lambda and mu. And another way of doing some experiments is with K and G. Now G is equal to mu. K is the bulk modulus, G is the shear modulus. So using those relationships, you can calculate lambda and mu, and then this finally gives you a relationship between your stress and strain. Okay. All right. So finally, the statement of the problem that we are trying to solve. Have we completed formulating our analysis problem? So if somebody gives us the geometry of our problem initially, they give us what loads are acting on our body, where B is again this a body force, meaning of some force that acts per unit volume. So that can be something like a self weight, or if your material is metallic and if you apply some magnet, that is also force that is acting per unit volume. And these kinds of things sometimes happen in electromechanical devices. P naught is this applied surface traction. So once again, I think I'll ask you all to distinguish between what are stresses and what are tractions. Traction is this kind of a force which is acting on a surface area. So if this is the surface of my bridge, and if I apply some force that is not necessarily perpendicular but in some general direction per unit area, that is called traction, and that is related to stress with our Cauchy relationship that says traction is equal to sigma applied on the normal vector. Okay, so once you have this given things, and let's say somehow you have done some experiments and you've also found out what is the relationship between stress and strain, that is your material model, then the final problem is to find phi or find equivalently u. If you tell me the map, I can find the displacement. If you tell me the displacement, I can find the map. And you have to find this map in such a way, and now this map, keep in mind, is the map of where does the big X go to the final configuration to the small x. This is a field variable that you have to find such that all these conditions, all these equations are satisfied. The first is your equilibrium equation, that the stresses should be symmetric, and epsilon, this is the strain displacement relationship. This has to hold at all x. At each and every point in your domain, it must hold. So in addition to that, why do we need boundary conditions? If we didn't have boundary conditions, we'd be solving this equation for the entire universe, right? So if we are going to restrict our domain, we are going to need some boundary conditions to specify what is called well-posedness of the problem. So here I'm defining this structure or this initial body as omega, and its boundary as this gamma. Now in the boundary, I've also denoted part of the boundary as gamma d and part of the boundary as gamma n. So what is that? Wherever you have a displacement that is specified, so for example right here, this would be a part of gamma d. Similarly here, this is a part of gamma d. Everything else is the boundary where displacement is not specified. So everything else is gamma n. This is just a collection of points on the boundary. What we are saying is that part of the boundary you have to specify some displacement, and if you don't specify some displacement, what happens? So you have this beam. Let's say you apply a moment, it goes to a deformed position. If you take the beam some other place, apply the same moment, you still get the same solution, but with a rigid body translation plus rotation. So that solution would not be unique unless you give me some points where the displacement of the boundary is specified. Okay. So the notation here is, okay, so another thing is that the total boundary should be equal to the union of those two. Since these are two sets, if we take the union of those two sets, put together those two sets, then I should get the entire boundary of my structure. In addition, those two boundaries, intersection of those two boundaries has to be equal to the null set. Now this phi is different from the map. This is a null element. So what this says is that you cannot specify two things at some point in the boundary. You cannot say that this point of the boundary must, let's say, displace by this much, and the force acting at that point is some value. So this is the intersection of those two pieces of boundary should be equal to 0. Now another some terminology here, gamma d is called Dirichlet boundary. Have you heard that word before? No? Anyway, this is just a naming thing. If you read it in your Hughes book or the Reddy book, you can relate that the Dirichlet boundary is nothing but the displacement boundary, and this is similarly called the Neumann boundary, meaning where where external surface tractions are specified. All right, so finally, the statement is that we have to find this map such that it satisfies all these equations at every point in our domain, plus it should satisfy this equation on gamma d. Now this equation says that my map or the displacement on my boundary has to be given to be some value. So for example, what would be let's say the value of gamma d or this function at this point at gamma d? So yeah, so one example for a specified function on the boundary is 0, where no displacement takes place. In this case, one component or two components of this bridge, if it's a three-dimensional thing, are set to be 0. The third component along the EX direction is free. So you can have parts of the components of your map also to be specified. Now the third equation says that if you finally find out what sigma is, and if you take your Cauchy stress, apply it to the unit normal at any point on the boundary. So you go to any point on the boundary, you find out what is the unit outward normal at that point. You apply your stress to that, what you should get is exactly P, the external traction applied at that point. So how would you come up with some function phi that satisfies all these equations? Is the statement of this problem. Now, another thing to note here is that the only critical unknown here is this map, or U. Once you have this map, you can find your strains. Once you have your strains, you can find your stresses from the material law here, and then you can solve for, you can check whether your equilibrium equation is satisfied or not. So the most critical thing that we are trying to find is this map. Okay. All right. So this is the statement of the three-dimensional problem. Obviously, for any general problem, even for this simple one rectangular beam, it is almost impossible to solve this in an exact manner, especially if there are steel and concrete mixed materials and all that. But so what we are going to try to do here is we are going to use obviously approximate means of solving these equations, but let's try to see if we can formulate a simpler problem in one dimensions first. Okay, so if I were to ask you something like this, again I have a wire and I'm going to apply some load P, which is let's say 10 kilonewtons, and the wire has some density and some area of cross section and all that. So what is the equation that, or how do I formulate this problem? This is a structure analysis problem. How do I formulate it in terms of what I just described? So what is the equation that I need to solve? Let's say this here is the y-axis, and this going down here is the x-axis. So given this geometry, let's say the length of the wire is L. Given this geometry, the material is, let's say again, linear elastic. So the stress, I'm writing it as a scalar because it's one-dimensional. So actually, given geometry, the load is given to be P, and in addition, let's say the wire or this one-dimensional bar is not of negligible weight. So there is gravity acting downwards, and the density of this wire is rho, and the area of cross section of this wire is A. And let's say there's no temperature effects for now. So what is, and the equation for the stress strain relationship is given like this. So what I'm asking you to do is find u as a function of x, where x is the coordinate. If this is the origin, x starts from here. You need to tell me what u is at each and every point along the bar, such that what is the equation that I should satisfy? The same equation that I gave you on your homework problem 1. So it is Cu prime, or actually let me not go there first. It is div s plus b in one dimensions. So that's sigma prime plus b is equal to 0. What is b? B is the body force, but what is its value? G or rho g, and actually rho multiplied with A multiplied with G, right? So this is the equation that I need to satisfy at each and every point along the bar. And I already know my material law. What are my, are there, actually, yeah. So what is the strain? Strain is equal to u prime. If you go and substitute in this equation right here, since all the derivatives are with respect to x, grad u is nothing but du dx. Grad u transpose is equal to du dx because it's just a scalar. Scalar transposes itself. Half of the 2u prime, you get simply this. Now another point to note here is that if you went with the full Green-Lagrangian strain, this would not be your strain measure. So the nonlinear strain measure, even in one dimensions, has this extra term sitting here which says u prime plus half of u prime square. But anyway, so all right, so this is the strain displacement relationship that also needs to be satisfied. In addition, there is this material law. So now what are the boundary conditions? Displacement at u is at 0 is equal to 0. So u at 0 is equal to 0. This is your gamma d. So this has to be held on everywhere for all x in 0 to L. And this has to be held on gamma d, which is defined as x is equal to 0. Similarly, the traction boundary condition is, what is that? Force at L is equal to 0, but what would that force be? P would, but yeah, how do I, what should I write? What is the similar equation here? How should I write this equation for this one-dimensional case? It says that sigma applied on the unit vector at L. The unit vector at L is +1. That's it. So sigma at L is equal to P. Now sigma at L, we know that it is equal to u prime at L is equal to P. So those are equivalent ways of saying that. So how do I solve this equation? Can I solve this equation? How should I go about solving this equation? Find u such that all these things are satisfied. So I can express this as Cu prime whole prime plus my body force, which is rho Ag, is equal to 0. If I take rho Ag to the other side, what that becomes is Cu prime is equal to minus rho Ag, which is just saying that d over dx is equal to this. Now I can start integrating it. Implies Cu prime is equal to minus rho A G x plus C1. C1 is the constant of integration. And similarly, if I integrate it one more time, what you would get is Ux is equal to minus rho Ag over C is this Young's modulus, x square over 2 plus C1 over C x plus C2. So C1 and C2, these two constants are unknown as yet. And the way we calculate that is from using the boundary conditions, right? So if we plug in u is equal to 0 into this expression, and if we plug in this equation, this expression into this equation, we can find out ux. So this is an analytical solution. We can, since this is such a simple problem, we are able to find an analytical solution, an exact solution. Exact solution considering this is not the exact solution to the real physical problem, this is the exact solution to the mathematical model. But going back to this, we cannot find a general, we cannot in general just integrate it and find these exact solutions. So from next time onwards, what we'll do is we'll take a look at this equation, we'll try to solve it in approximate ways, and then we'll try to extend that, those ideas to 3 dimensions. All right, so let's meet on Monday, and I'll assign a homework 2 today. By the way, the homework 1 is due 10 p.m. today.